All right, welcome to another Chapter 6 video. When to use rational exponents. And I'm going to go ahead and do this first example here. So what I have written already in black is already there. So let me just kind of write on top of this in another color. I'm not going to use a rule here. I'm just going to, well, use a rule just to do what it says. So square means x cubed times x cubed. I'm just thinking squaring something means to write it twice. And then this, well, that's 3 of a kind, that's 3 of a kind. So in other words, it's literally x times x times x times another x times x times x. And of course, I get x to the 6th for that calculation. And that calculation is fine, I suppose, if you have like a 2 and a 3, like I had here. But in general, there's a rule that I think you should know at this point, and that is you could multiply the 3 and the 2 together, and that's how you come up with the 6. And the reason why this is important is it's not always going to be a nice number like 2 and 3. It could be a fraction, it could be something else. So know what to do with the exponents. But I call this an old rule because it's a rule that the book has been using since certainly before Chapter 6. But the new Chapter 6 rules are over here, and they are, you can take the square root of a and rewrite it as 1 over, a to the 1/2. The nth root of a and write it as 1 over a to the 1 over n. And even if you have this fraction here, well, the eventual fraction here, if you have nth root of a to the m, you can write it as m over n. So n is the index, we call it. That's going to be in the denominator. The invisible 2 in the index here, it has to be visible when we write it in the denominator here. So you get the idea. So these are new rules for Chapter 6. And by the way, we call this a rational exponent. It's like a fraction. Anytime you have a fraction, we can call that a rational number or whatever the things we're talking about are. So I want to do this problem, and let's keep in mind that we know some rules for exponents already. So our goal is not to come up with new rules. In other words, you probably could look up online and find some rule to do with the 3 and the 4. We could maybe discover one, but the whole idea moving forward here is to use the rules that we know rather than create a bunch of new ones. So the rule I just talked about, this x to the, or the cube root of x can be thought of as x to the 1/3. And because that is nested inside this other radical, I can think of the outside radical, the 4th root of x is x to the 1/4. And do you remember what we're supposed to do in this situation? I just had it up here. Right? Multiply the exponents. So if I didn't write these as rational exponents, I wouldn't be able to, I wouldn't know that I was supposed to multiply them together. So this process of converting it from radicals to exponents, let us take advantage of a rule that we've known for a very long time. Well, when I say we've known for a very long time, we've known it in this format for a very long time. And it allows us to answer this, to get this far in the problem. Now, I'm not done. Generally, if you start with radicals, you want to finish with radicals if you can. Now, if the answer just doesn't have any radicals in it, that's fine, but I really should do this last step, and that last step is to convert it back into a radical. Now you might see you might be onto something. You might say, well, should I have known that I could multiply the 3 and the 4 together and just get this answer? The answer is no. We're not trying to create a whole new set of rules for radicals. We want to use the existing rules, and that's good enough. All right? So there is no intermediate algebra book where you would see a list of rules for radicals and going straight all the way from here to here. In pretty much every intermediate algebra book, they'll tell you do the conversion, use the rules you have, and convert it back. So we really are using rational exponents, but we're not finishing with rational exponents. We're just using them because we didn't want to learn a whole bunch of new rules. All right. My last example of that is this question where they want us to write this as a single radical. Now this is a fairly challenging question, so be prepared here. It's a little bit of work, a little bit of thinking we got to do. But and I guess the first thing is to think about is how can we combine these? Now notice the indices are different. If they were the same, I could combine them, and actually that's the secret to getting this problem done. I need to make the indices the same. And if you follow the reasoning here, that's the same thing as making the denominators the same. So I'm going to go ahead and use something that we know here. Going way back, I can change 1/3 to 2/6. And I can change 1/2 to 3/6. Again, the goal was to make the indices the same, and that means, in this case, I needed the denominators to be the same. So basically, the same skill you use to add fractions, we're just applying it here. So that's 6th root of x squared, 6th root of x cubed. And I just want to shout bingo at this moment because a very significant mission has been accomplished. I had different indices, now they're the same. Well, if that's true, I can put it all under one expression and add those exponents together. I get the result. So I warned you, not an obvious result, and this is probably a good explanation, just a good example of why we don't try to do all of the work within the radical notation. Just too many steps, and the answer is just too weird to come up with a formula that would just shout this answer out in, directly from here to here. Why is that the answer? Well, all of this is the explanation. Because x, the cube root of x can be written as x to the 1/3, and I just used known principles throughout the book, at least from here to here, and it was only the conversion that was kind of new to chapter 6. So let me roll back here. These conversions sometimes pay a huge dividend. You can't do much with a problem. Change it into its rational exponent, and then you can. All right. So that is when to use rational exponents as part of chapter 6.